Hi, everybody. I'm Kyle. I'm a postdoc now at UC Santa Cruz. Although the results that I'm going to show off today really stem from an exoplanet imaging survey that I carried out as a graduate student, following up stars that show small astrometric accelerations between Hipparcos and Gaia. Let's see if this works. Okay. So over the past couple of decades, through a ton of hard work, the exoplanet imaging community has done an amazing job assembling a sample of about 30 directly imaged giant planets on wide orbits and about 100 or so brown dwarf companions. As we heard about or as we saw in sort of Dino's talk, one of the main motivators behind this effort is answering this question of how these objects form, right? These widely separated super Jovian exoplanets often live in a gray area, where it's not immediately obvious whether they formed through some traditional bottom-up core pebble accretion formation process, a top-down scenario involving gravitational instabilities and fragmentation and massive protoplanetary disks. And some of these widely separated planetary mass objects might actually be the lowest mass products of the star formation process. And so determining how these different formation channels combine to produce the population, the sample of giant planets and brown dwarfs that we observe is one of the main drivers behind exoplanet imaging efforts. Now, in order to diagnose and test these different formation routes, we need to understand the kinds of objects that we're discovering. But a challenge is that for most imaged planets and brown dwarf companions, their masses are highly uncertain. So this plot here shows the sample of imaged brown dwarf companions, the masses and orbital separations of the sample of imaged brown dwarf companions in gray and imaged exoplanets in orange. Now, for most of these points, their masses aren't directly measured, but instead we have to infer their masses from their luminosities and their ages using evolutionary models. And the problem here is that these mass determinations then hinge on the specific model that you adopt in their input assumptions. And so you might not be sure whether you have a 5 Jupiter mass object or a 20 Jupiter mass object. But as we march to closer in separations, the reflex motion that objects induce on their host stars gets larger. And so this has been used, especially in the last few years, to obtain direct dynamical mass measurements for a small sample of mostly brown dwarf companions, as well as a handful of planets. And these benchmark objects really offer us some of our best windows into the formation of substellar companions. As for one thing, their masses are pinned down directly. That contextualizes these discoveries. But also we can use them to test the evolutionary models that we use for everything else in their input assumptions about planet and brown dwarf formation. But if we really want to understand planet formation through these dynamical masses, we really just need more of them, right? You can see that we've just scratched the surface so far in the planetary regime. So how can we expand the sample of imaged exoplanets with dynamical masses? Well, as we heard about in Mona's excellent talk yesterday, astrometric accelerations between Hipparcos and Gaia have proven to be a really effective strategy for sort of tilting the odds in our favor of imaging new exoplanets. So the idea is that a wide-orbiting planet or brown dwarf companion will induce a small proper motion change over the 25 years between these two all-sky astrometric missions. And so one can use this to conduct an informed targeted search for planets that we can image by specifically focusing our search on stars that exhibit this kind of dynamical evidence of the presence of planets. And an advantage of this approach is that then enables the measurement of these direct dynamical masses. But how do we pick the best targets for an exoplanet imaging search? Given an astrometric acceleration, we can determine the companion masses that are consistent with producing it as a function of separation. That's shown in the blue curve here. And so it sort of has a characteristic shape. You have a power law wide separations that flattens out as companions crack out more of their orbits between Hipparcos and Gaia. This plot here actually corresponds to the host of a benchmark brown dwarf companion. And so if I plot up its dynamical mass and its separation, we find that it lines up quite well with this prediction. And so the point is, with these predictions in hand, we can really quickly and effectively triage potential targets for an exoplanet imaging survey. And so over the last several years here, I've been leading an exoplanet imaging survey informed by these astrometric accelerations. This is a survey that we've carried out primarily with Keck, with NERC2 on Keck. We've also had sphere observations, Skexio and Charis observations. And the whole kind of guiding light of this survey is maximizing our efficiency for making new discoveries. We focus on young stars, which give us the most favorable contrast ratios for imaging planets from the ground. And so I'm currently at the kind of later stages of wrapping up and publishing the final results from this survey. I can show off. So we've obtained NERC2 imaging, high contrast imaging sequences for 25 accelerating stars. We've been hard at work optimizing the reductions of these sequences and are looking forward to publishing all of this data out into the community in the next couple months here. So what science has stemmed from this significant effort? Well, a couple of years ago at the Keck Science Meeting, I talked about this discovery, 21152b, the first imaged brown dwarf companion in the Hyades cluster. This is a companion that was independently discovered as well by two other teams. That's been kind of a theme for the style of targeted high contrast imaging search. It has a separation of a little under 400 milliarcseconds, an L-band contrast of 9 magnitudes. It's orbiting a host star. It's a little bit bigger than the sun in the Hyades cluster, which gives a precise age constraint at kind of an intermediate level of 650 megayears, which is really useful for comparing its dynamical mass of 25 Jupiter masses against the predictions from evolutionary models. And its dynamical mass is actually a little bit lower than the predictions from hot start evolutionary models. They don't always exactly line up. And the astrometric acceleration signal here that points to the presence of this companion is 8.5 meters per second per year. So I'm going to spend the next few slides talking about the second discovery from this program, which is AFLEP-B. AFLEP-B is a directly imaged exoplanet that we discovered through our program that's the lowest mass imaged planet with a dynamical mass measurement. We first imaged the star with NERC2 and Keck in December of 2021. These observations used the vortex chronograph, by the way. And then we followed it up about a year later. And you can see the amount that the companion's orbit tracked out over that intervening timescale. And one of the more kind of exciting elements of the discovery of this planet was that 3 teams at around the same time with different instruments and time baselines all sort of arrived at this same discovery. And so this has meant that this planet has been really well characterized right from its outset, right from its discovery. We, of course, imaged the planet with NERC2 and Keck. So we got L-band photometry of the planet. It has an L-band contrast of 10 magnitudes. It's orbiting a sun-like host star in the Beta moving group, which gives us precise age constraint of 24 megayears. AFLEP-B follows in a tradition of planets being imaged around stars that host debris disks. The astrometric acceleration signal that led us and other teams to image this star is 2.5 meters per second per year. And then, of course, the big result, so the dynamical mass of this planet is 3.5 Jupiter masses, which places this planet as the lowest mass imaged planet where we have this kind of direct measurement of the mass. And so since this discovery, AFLEP-B has been rapidly characterized by the community. We actually saw some kind of results that are about to come out from Dino's talk, but there's also been dedicated retrieval studies of the atmosphere, forward modeling of the atmosphere, recovery of this planet and archival NACO data from 2011, JWST observations of the planet, gravity observations of the planet, high-resolution spectroscopy of the planet. It's been really remarkable to see how the exoplanet imaging community has been able to characterize this discovery made with Keck. And I'll just sort of take a beat to note that some results from a JWST program. This is a cycle 2 director's discretionary time program that I co-led with William Ballmer, where we recovered the planet despite it being at 320 milliarcseconds away from its star, which is like readily done with Keck, but for JWST, that's 2 lambda over d away from its host star. But despite this, we were able to robustly recover the planet. And in case you're not convinced that this is a challenging detection, this is where the inner working angle of the chronograph is. So the throughput of the chronograph at this planet separation is 7%, right? We're losing more than 9 out of 10 photons to the chronograph that we used here. It also occurred to me during Chaz's talk, by the way, that this is a really clear demonstration of JWST science that has stemmed from NASA Keck time. So as I mentioned, this planet has been robustly and well characterized with a bunch of different instruments, actually both before and after its discovery, with this archival recovery of the planet from 2011 NACO data, with the planets on the other side of its star. It took that 10 years to orbit to where it was in December of 2021. There's also been gravity observations and spectroscopy of the planet. And so a comprehensive picture of this planet's properties has emerged. The planet has elevated atmospheric metallicity, a semi-major axis of 9 AU, similar to the semi-major axis of Saturn, a circular eccentricity, an orbital inclination that closely matches the projected inclination of the host star, so some signs of potential spin-orbit alignment in the system, a dynamical mass that agrees with hot start model predictions or warm start model predictions if the planet took a little bit of time to form. And all of these kind of trends are reinforcing sort of already established or emerging trends among the broader sample of imaged exoplanets in metallicity, eccentricity, and spin orbital alignment. When we start to sort of pull all these lines of evidence together from the circular orbit, an orbital inclination consistent with spin orbital alignment, a semi-major axis at the peak of gas giant production, a dynamical mass of 3 to 4 Jupiter masses, and enhanced atmospheric metallicity, these lines of evidence are suggestive of the planet forming through a core accretion formation process. And so to go from the discovery of the planet 2-ish years ago to assembling such a well-mapped SED and orbit to be able to make this kind of inference about its potential formation really speaks to the science that you can do with this style of informed direct imaging survey. We sort of zoom out to kind of take stock of the full survey. Out of a 34-star sample, folding in sphere and Paris imaging, kind of taking the young subset of the sample, we've discovered one new planet and one new brown dwarf companion, which is about an order of magnitude smaller in terms of sample size than if we don't have this sort of astrometry-informed survey. So our assessment is that we're estimating an improvement in discovery efficiency by 7 times over a blind search. But an important caveat that I should note here is that we're intentionally biasing our survey, right? So if the goal is to discover new planets that we can characterize their orbits, their atmospheres, this has been really great at increasing the count of discoveries. But you lose all the demographics information when you have a large unbiased sample. And so this is really exciting, and I think it leads really well into the future for this style of informed exoplanet imaging survey. Because the next data release of Gaia is currently expected to come out in December of 2026. And that's expected. So this plot here shows the sensitivity right now to planets around AFLEP. And so anything above that blue curve would produce a 3 sigma or higher astrometric acceleration. Here's what happens when we move from Hipparcos and Gaia DR3 to Hipparcos and Gaia DR4. It pushes the sensitivity down to lower masses, sort of across the board here. And so that'll open up additional targets for this style of informed exoplanet imaging search. But also here's the regions where we can detect planets just within Gaia as sort of acceleration solutions. And so all of a sudden, any targets that are too faint to be in Hipparcos, which have been off the menu for this type of informed direct imaging search, will suddenly become fair game. And I think Keck is really well positioned to sort of clean up in this world of new informed targets or astrometry-informed targets with instruments like HiSpec and Scales, HACA, a pyramid wavefront sensor, all kind of in the works for sort of the plus or minus 1 year timescale with the DR4 release. So this is very exciting. I'm very excited. I think that this is really promising and that Keck can really play a leading role here. Thank you.